Example 7.7 or 8.7 for the given textbooks. For details, please see the description below. Liquid methane is commonly used in various cryogenic applications. The critical temperature of methane is equal to 191 Kelvin, and thus methane must be maintained below this temperature in order to be kept in liquid phase. The properties of liquid methane of various temperature and pressures are given in this table. We need to determine the entropy change if liquid methane as it undergoes a process from 110 Kelvin and 1 megapascal to 120 Kelvin and 5 megapascal. The analysis must be done using the tabulated properties in the table, as well as approximating liquid methane as an incompressible substance. Once we do these calculations, we need to determine what is the error involved in case B. These are the information for temperature and pressure that we have for the beginning and the ending stage of the process. Using these tables, we are able to find the values for CP and entropy at both of the stages. First part is asking us to calculate the entropy using these tables. So we're able to find the change of entropy simply by taking the difference between of the final state minus the initial state, and that is simply going to be 5.145 minus 4.875. Both of them are in kilojoules kilogram Kelvin. Therefore, the final value is going to be 0.270 kilojoules kilogram Kelvin. Please note that these values come from a table, so these are the actual values for the solution. The approximation is going to be done by assuming that this is an incompressible substance. In that case, we could approximate the change of entropy to be simply the average value of CP times the natural log of the ratio between the temperatures. So we have two values of CP, then we're going to find CP average, and that is simply going to be 3.471 plus 3.486 divided by 2. Therefore, the average value for CP is going to be equal to 3.4785, and this is going to be in kilojoules kilogram Kelvin. We take this value and we replace it in the equation. So this is 3.4785 kilojoules kilogram Kelvin, and then we multiply by the natural log of the ratio of the temperatures. This is equal to 120 Kelvin divided by 110 Kelvin, and we find that the change in the entropy is going to be equal to 0.303 kilojoules kilogram Kelvin. If we do a percentage difference between the approximation and the actual value, we find that the percentage error is equal to 0.122 or 12.2%. Notice that this approximation evaluates liquid methane as an incompressible substance. Incompressible indicates that the value of the density remains constant. So let's evaluate how the density changes between these two states. We have 1 megapascal at 110. We have a density of 425.8 kilograms per meter cubed. Then if we go to 125 megapascals, we find the density to be 415.2. This is a difference of about 3%, which is not a high value for a difference, which allows us to say that yes, we could treat this as an incompressible substance. The difference that we have in the entropy, it's 12.2%, which is not an extremely high value. It provides a valid possibility if the tabulated data is not provided for cases such as this one.